So we're going to do Dilantin here. So I'm going to kind of jump around a little bit. I'm doing both the Dilantin discussion and the benzyl one, which I just did. So I got all the paperwork kind of here. So let's just start with, interestingly enough, and I'm just realizing Dilantin when I ran the UV, okay? Notice how I have one peak and it's at 202, right? You don't see much else here. Now moving to, this is a previous year's, hence it's already marked. Urea, kind of looks like that, that's fine. But look at their Dilantin. I understand the 202 peak, right, which would trail down here, matches this one. So obviously there's some leftover other material giving a UV absorption right there. So this person's UV, especially when you compare it to, let's just say somebody had pure recrystallized or a pure product, and it clearly had this. So clearly there's a difference, and this has some other stuff in it. But anyway, the UV looks like that. Benzyl, I actually didn't have, so I don't have that one to show, but again, that's more for you guys just recording it. IR, urea, which looks like that. I don't expect you to assign it, you know, but at the same time, I think this is pretty simple, right? There's no carbon with hydrogen stretches. All you have is nitrogen with two N stretches, so that's what these are. And then the carbonyl absorption is likely the 1681. And then these right here are the NH bend. So that's easy enough for that one because it's a small molecule. Now Dilantin. So Dilantin, and again, the rule is you must always draw the structure. You must draw. Drawing while looking through a camera and holding it is kind of funky. And we have an OH. I'm supposed to take a mark off the top automatically if you don't draw structures on your spectra. So we already know how this rolls. Interestingly enough, we are led to believe that right here, and I know this has some tautomers. You might see something else that puts a carbonyl here, and the lone pair jumps on here, or that H moves over here, right? So you might see other drawings in tautomer form that look like this. So this would still have an H and this would have an H. So I guess what they're really indicating here is, now clearly, if you drew this structure, you could say that these two peaks, one is this one and one is that one, the NH or the OH stretch. If you drew this tautomer, you have two different NH stretches. I don't care which one you do. These are either this drawing's stretches of H's on O or N, or this one on both ends. Then what you have is you have a little bit of a mixture of some peaks in carbonyl territory. If we drew this one, these two carbonyls are different, so it makes sense that you have to see at least two absorptions for sure. So that's probably one way I would do it. I would look at this tautomer and say, look, two of these are likely to be these two different carbonyl stretches. Then you have phenyl groups. So you could look at, well, this 1590 is really small. Probably buried in here is another 16, but anyway, you could circle some of these, call it aromatic carbon-carbon stretch. Mono-substituted rings, I guess I could circle these two and call it that. We already did the benzyl, so you can refer back to that video for that. We did the benzyl NMR. By now, you guys should definitely be able to look at that. So let's look at the proton for Dilantin. So if I'm going to finish writing this tautomer on the proton, and again, I recommend you guys practice drawing through the camera. So it would look like this. So whichever one you wish, that's a phenyl, and this is a phenyl. So clearly, whichever one you want to use, this one would show an H on O or an H on this end. This one has two different H's on an N, but they're different by symmetry, so you expect two. So this is what it looks like. One of them is this one of them is the other. So each of these is going to be either that H in this one or that H in this one. The rest, which is this group right here, is all of the remaining hydrogens on your phenyl rings. So you've got 10. So roughly, this integration's 11, and this is each 1 and 1, so it's very close. This is a nice looking spectrum. It's clean, so you scan along. You might see a little bit of, one of these is going to be water for sure. The other one we don't know. So one of these has a little bit of water. If you take this crude, don't forget when you isolate your dilantin on the first day, there's a lot of water. So some of you might see a giant water peak, so be careful of that. Carbon-13 looks like this. I'll let you go ahead and start label. Well, the carbons would be A, B, C, D. Let's go with an E, F, G. So, carbonyls. Let's see if we end up seeing, if it's this structure, clearly you're going to see one carbonyl officially. And it's interesting, it's an amide one, and it shows up right here at 175. The next one is 155. So clearly the carbon is indicating this structure is preferable, quite frankly. The aromatic rings, you'd see 1, 2, 3, 4. You should see a short one, which is here. There's another short one, but we realize even this has another carbon, G. So G and D means I should see two short ones. There's one here, there's another one right there. This is mid-range, probably A, and then C and B would be these two taller peaks. You've got here at 70, right there, that would be carbon E. So that takes care of that. We'll go to this discussion. The mechanism is online, folks. Everybody has it. Someone's book from last year has, I mean, look at this. You find this online and it shows you all the intermediates. So what I'd like you to do is simply say, look, we know urea and benzyl is down here. Dilantin is highly more functionalized, so it should be, for organic material, higher in energy than the starting materials in the organic compound sense. We know base is much more reactive, it's up here. And the mechanism, if you want to, you should find out what intermediates are in there. You could draw those steps in between, right? So the question is it overall endothermic? It's very likely. We know that OH base is not super aggressive. So it's likely to be endothermic, and that's why we're heating it, right? The other thing we've noticed is part of your procedure says dissolve the solid up front. It said wait till this dissolves before you heat it, but we find out that in organic, you throw it all in the flask, you heat it, and then it magically turns liquid. So first off, they're mentioning a problem with a solid not going in, and then later, when you're done, it says if you have white solid, filter it hot, right? So right away, they're calling to your attention to some other white solid. Now, most people don't have this filtering, but then your final product has a notorious problem, especially when you go to recrystallize. A lot of times you see a very grayish white other compound that seems to be in there, and it interferes with trying to purify your dilantin, right? The interesting thing is sometimes when you're supposed to get a carbon-13, some people get a lot more of this mysterious other grayish white product. It does not show up, so it's likely inorganic. So if you're trying to make a very concentrated NMR sample, you're not getting that done. So this is part of the problem why. So in a discussion, you have to talk about this possibility and how you might want to get rid of it.